DevOps is short for Development Operations. It focuses on a collaboration between developers and other roles. Developers typically work in isolation. They can't do this anymore. We need to work in conjunction with the operations people and the QA people. We need to find out how to develop an application from start to end, from the inception all the way through to production and production support. It's about thinking about how things are going to work in the future when we're in the very beginning stages of the operations. And the great importance is on automating the process. We don't want to do things manual anymore. We want everything to be fast, totally automated and reliable. The number of issues facing DevOps. Software requirements are constantly changing. We also need to define a good path between design, development, testing and release. We need to decide how to package the software, how to distribute it and how to deploy it into production. And we also need to have ongoing operations and running the system from the future from once it's deployed onwards. There are a number of deployment issues. These are particularly true in the case of web applications. Traditionally, developers write the code and operations people manage the servers. When it comes to things like application servers, there's a gap because there's a thing called a deployment descriptor which is neither in the developer's realm nor the operations realm. We need people who can bridge that gap if we're going to be successful. So because developers have very little knowledge of the application server, they only know about the code and they're only interested really in the code. The actual workings of the application server can be a bit of a mystery. The operations team are not usually developers, so they don't know how to interface the software with the application server. So we need people who are both developers and operations people to resolve the issues. This is what DevOps is partly about. Now, the whole process of DevOps is to use automation and use different tools to do the operations. There are a number of different categories of tools. Each of the categories has got its own range of tools which each do something similar but in a slightly different way. So for example, we've got tools for monitoring, we've got tools for releasing into production, configuration management, packaging the application, all sorts of testing, integration and performance testing, building the application and initially starting with the code development and unit testing. There's a whole range of tools and we'll be looking at the whole range of these tools from one end to the other. So, what are the goals of DevOps? It's about thinking about the whole system, the whole process from start to end. This involves coordinating with the teams and involves having feedback loops from one position to another. It's also about continuous improvement. We need to improve the way we work by working well together and using the tools correctly so that we have fewer incidents in production which have costly repercussions. We also want to improve the process efficiency so that the team learns and is better and better each time. So, some important improvements are these. Reducing testing time. That doesn't mean reducing testing, it means reducing the time that the tests actually run. Try to reduce the amount of changes required. When the requirements are conflicting or incomplete, we need to resolve those conflicts early on. We need to find the simplest solution to meet the requirements. It's not necessarily the optimal solution, but a best solution that works well. We need to use standard tools across the organization which integrate well together. We need to have really robust production systems which have very low maintenance costs and are very, very reliable. We also need to produce software to the highest possible quality. And to achieve this, we need to improve the performance of the individuals and the teams and how they work together. Now, part of the process of improvement is changing the way people work. We need to strive for clarity. We want to challenge any uncertainties in requirements. We don't want to fill in the gap, which many people are tempted to do. Ask somebody who knows what the answer is before making any assumptions. Assumptions themselves are particularly difficult to deal with. We need to be sure that they are valid assumptions and that they haven't been put there for some reason which hasn't been justified. We want simplicity and reliability. The optimal design is almost impossible, but the best design is what we'll strive for. We also want to reduce risk. We need to be able to meet the requirements with the least risk path. And an important thing is to avoid gold plating. Don't put extra code in there just for the sake of it or for some potential future change which may never happen. Do the minimum to get the thing to work. And when there's an issue, Find the root cause of the issue. Don't just try and fix the symptoms, because the root cause is going to come back and bite you later on. So the working practice should be constantly evolving and very iterative. So you learn something, some new technology, some new tool, you try it out, work with it. Then you think about it. Okay, did I do a good job of this? Could I do a better job of this? How could I do a better job of this? And then you learn some more to improve yourself and go round and round the loop as you improve as time goes on. So that's the end of that section, and now we've got a knowledge check. Now we're going to look at the technical challenges, of which there are many, and DevOps is really here to help solve these technical challenges. So what are these challenges? Well, first of all, technology is constantly evolving. If we look at the IT world, in terms of software itself, very little has changed over the last 30-40 years. We've just got better at it. But the technology has changed dramatically. No longer have we got large rooms full of very hot, expensive machines. We have very small, fast and efficient machines these days, and we have to be able to use this technology to its best. Our working environment is changing as well. We've learnt over the time how to do things better, and we've got more interesting working practices these days than we've ever had before. Good practices 5 years ago are now considered bad practices. This is constantly evolving. There are also external influences over which we have no control. A news story can cause major economic incidents. There are legal effects. Some industries, particularly the finance industry, is very, very tightly regulated. And there's also social influences as well. We need to keep our customers happy at all times. So DevOps is a culture which we need to build and maintain. It needs to adapt to continuous change by continually changing. And the organisation's culture needs to evolve around it. The problem is, people are very resistant to change. They don't like to have to do something in a different way to which they're used to. But also, we need to get people to work together and not in isolation. Some people do not like this. They like to work in a box, quietly sitting there with their headphones on, not interacting with anybody, just focusing on their work. We really can't do this anymore. We have to work together. We need to talk together and get together to get a good solution as a team. Now, software tools are very important for the whole process of DevOps. Now, individuals and teams will have their preferred tools. In a large organisation which has been formed by mergers and acquisitions, the teams will have come from different parts, and they will have their own different set of preferred tools. We really can't do this. We need to have a standard set of tools across the organisation. Open source tools are readily available, although some organisations don't like to use open source tools because of support issues. But it's also important to have a very standardised set of tools across the organisation for various reasons. So look at the reasons. First of all, licensing and compliance. And many of the software applications and tools require licensing. That can get incredibly complex for a big organisation with a very wide range of tooling. We also have problems with versioning. If people are using different versions of the tools, there are going to be compatibility issues, which you need to address. There's also very important that there are production support for the tools. You can't introduce a tool into a production environment if the production support team can't support it. And we also need to think about the future. Once an application is in production, it needs to be maintained and supported, and it needs to be easy to do that. So many organisations have legacy systems. And any new tools which are introduced need to be able to function with both the new and the old systems. We're getting to the stage now where we're getting hybrid environments. We have the existing solutions, we've got new cloud-based solutions which are increasingly attractive because of the cost values, and tools must be cloud-ready or cloud-compatible for future deployment. The old and new systems need to work together and complete with production support for both old and new systems. Corporate networks are very important, and they're getting increasingly complex. We need to address issues such as internet connectivity. We need to think about the addressing of various machines and firewalls. We need to have virtual local area networks across sites. We need to connect to the cloud. How about the data centers? Where are the data centers and how do we connect to them? And also think about the local area networks on the company sites, keeping teams isolated from each other so that they don't have access to each other's data if that might not be a good idea for various reasons such as security. So changing the network configuration is very complex. It's also very risky because you're likely to break connectivity. Cloud computing comes with its own networking, which is actually very efficient. It makes things less complex, much more adaptable, and more auditable. It also needs to be more secure, but cloud platforms are very secure by default. Everything is denied by default, which is always a good thing. You have to open up access to give people permission to do things. There's also a cost impact. Changing corporate culture is costly. We need to buy new hardware. We need to buy new software licenses. We need to pay for cloud usage, which is usually by resources like CPU and network. We need to retrain our employees so that they understand and use the new equipment and tools very well. People are learning new skills. We do run at reduced efficiency, but we have to live with that. So there needs to be a budget for ongoing change. We need to know it's going to cost. There's going to be an initial cost in terms of efficiency and quality, but that will improve over the long term. So DevOps is not just about writing and deploying code. We need to improve existing code. New tools need to support new code. New tools need to support new code, but they also need to be able to support legacy code. Legacy code might need to be changed or restructured over time to make it more manageable and to make it fit in with the new process and tooling. And we need to take on board bug fixing enhancements, which need to work with the new tools and new procedures. Now, so let's have a look at some of the software tools. We'll be looking at each of these tools in more detail later on during the course, but let's have a look at what the actual basic tools are. So we have the concept of a tool chain, and one of the challenges is to select the right tools. There are many tools that perform similar functions, and the tools also need to work very well together. And there are a number of categories of tools, for each stage of the software development lifecycle phases. Some tools straddle various phases, some are very specific to individual phases. So let's look at the first stage, which is requirements analysis. And it's all about communication within the team and talking across different roles. So we need to be able to allow developers, managers, customers, business analysts all to talk the same language. And think about the various tools that we want to use. So fairly obviously, word processors and spreadsheets, although spreadsheets are often very much abused and can cause a lot of problems. Shared calendars, so we know when meetings are. Sprint management tools, although a lot of sprint management tools are very low tech. Wikis are incredibly useful for storing information which is readily accessible. We need UML diagramming tools to describe our applications, and we need issue and task management tools to manage the workflow. We have the concept of artifact creation. An artifact is simply a byproduct or result of some operation on some kind of code. So very important to source control systems. They manage the versioning of our code and make sure that we're building the right thing from the right versions of the software. We've got continuous integration tools, very important for detecting problems early so that they can be fixed and so they don't delay other developers' work. We have build tools which assemble the components of our software from source code through the various artifacts to the production executables. We also need to gather documentation information, and there are tools that do that. The most complex stage of any software development is the code development stage, and there are many tools that are needed at this stage. There's a variety of different editors. We need different databases, different types of databases, different tools for building the software. We need tools for code review. There's also very important code quality tools which can assess the quality of the code and identify common problems very quickly. We have various things like REST API design, and that's a very difficult thing to do. Develop an API for communicating across a network using the REST APIs is very, very difficult to coordinate. User interfaces are also incredibly difficult to describe and get to work well. We also need to be able to map code to databases. We need unit testing and mocking frameworks to make sure that our code is fully custodied. The very important integrated development environments, they save a lot of time. Developers effectively have an operating system for which they can develop code without having to go outside of it. And then of course we've got the compilers and interpreters which tend to just work behind the scenes, turning our code from source code into executable code. Testing is vitally important. We start off with unit testing and mocking frameworks for doing test-driven development. We've got scripting for writing more advanced tests such as integration tests. We've got test harnesses which test full systems and partial systems, and we've got user interface playback tools for testing web interfaces. We've also got packaging tools. We have repositories where software is stored which we can fetch and integrate with our system at any time. Build tools appear here again. We've got container management tools which are increasingly important. People like the use of containers where you have one application per unit of deployment which can communicate with each other. And then we've got the deployment descriptor generation tools, which is also very important because deployment descriptors which describe how software interacts with containers are very difficult to write. Then we've got release management tools, which are also very important. Change management systems. We don't make change into production unless it's been fully documented and approved. We need approval systems to approve releases. We need to have important rollback mechanisms. If we deploy an erroneous system into production, we need to get back to the previous version as quickly as possible. We need to automate the process of release. We also need to be able to schedule tasks so that we can run various components of the system at the right time and in the right sequence. And the important enterprise integration tools, which allow us to deploy and change applications dynamically, automatically. Very important configuration and monitoring tools. Infrastructure configuration and management. We don't want to do it manually, we want it automated. We have the concept of infrastructure as code, basically scripting which controls the infrastructure. Request tracing tools. Find out exactly what happens when a request is made, is it being executed and put into production. Performance monitoring is vitally important. Make sure our systems are doing what they're supposed to do in a timely fashion. Also log file analysis tools. Many systems produce a lot of log files. The output is very, very verbose. We need to look for the interesting things, which are usually things going wrong, which are very small parts of the logging. Then we need to be able to report issues as soon as we can detect them and have the processing mechanism in place to deal with them. So now we're going to look at cloud computing. It's getting increasingly important to deploy things into the cloud, as the cloud gives us many benefits, including cost and performance. Traditionally, companies had data centers, but data centers are very expensive to run and maintain. For a start off, you've got to have a building, and the building needs to be maintained, and it has to be purchased. We've also got to buy vast quantities of computer hardware. That's expensive. We also need considerable power supplies. Large data centers consume vast amounts of power. And anything that uses vast amounts of power gets very hot, so we need a good cooling supply to do that. We also need physical security. We don't want people getting into our data center and causing problems. We need to make sure we can connect to the data center from anywhere in the world that we need to. We also need to have maintenance teams to support everything because hardware fails fairly frequently and we need to get it fixed as soon as possible. We also need to have security teams in place to check that everybody's got the right access and nobody has unauthorized access. But that means we've got to have policies and mechanisms in place to secure our data centers. So it's a very expensive thing to do. To give an example of failures, the standard SATA hard drive has got a mean time between failure of 1.2 million hours. That's a long time, it's several years. But if you think about it, a data center with 100,000 hard drives, the laws of statistics, if you multiply those numbers together, it says you can expect 2 drives to fail every day on average, which is quite staggering really, isn't it? Most people don't expect hard drives to fail, but if you've got hundreds of thousands of them, they're going to fail. So what have you got to do? Well, for a start off, you've got to have a supply of replacements to replace them quickly. Every disk needs to be mirrored so that if it fails, it's taken over by another one. We need to detect a fault and be able to find it. If you've got a data center with 100,000 hard drives, how do you find the one that's failed? We need maintenance teams who can deal with these problems, locate the faulty drives and replace them. We also need to be able to destroy the disks correctly so that data is not gained by other parties. For example, destroying the disks completely so that all data is definitely lost. So rather than having a corporate data center, we move to the cloud. What happens is cloud platform providers have invested very, very heavily in infrastructure. So what they've got are very, very large data centers, very highly scalable environments, very secure and very reliable. And they provide a number of services. So on a cost basis, you can choose how much disk storage you want. You can decide how many CPUs, how much computer power you want, what services you require, what platforms you want, particular operating systems, and also what applications you require. So one thing that these cloud providers do is focus on doing one thing very well. They provide a computing platform. They're not interested in anything else. It's the users that provide the rest of it. So a bit more about data centers. Cloud providers have very high performance data centers. They are geographically distributed around the world. It is actually quite important, this. Some organizations are required by law to have their data in certain places geographically. So data centers will be distributed typically several per continent. You need to have access points in many locations. We need to have high-speed networks connecting from wherever you happen to be to the data centers. Within the data centers, there needs to be extremely high-speed fiber cable connectivity between the machines. And many cloud vendors own their entire infrastructure across a global network. They also have edge caching, where information is stored at the boundary where the users interface to the cloud, rather than deep inside the cloud where the actual data is stored. So there's a concept of infrastructure as a service, or IaaS. This is the basic power that is provided by the cloud providers. So you've got raw computing power. Choose how many CPUs you've got and what power CPUs you've got. Raw storage, how much disk space do you require? What kind of networking do you require? Do you require an external IP address? And then the ability to build a computer or network computer virtually. You provide the parameters in a web page and the system will just build you a computer within a matter of minutes. So obviously the cloud providers want payment. And how does this work? Well, typically payment is by resource. So when you use a component, nobody else can use it, so you're tying up that resource. So basically it's fair to pay for components when you're using them or when your resource is held. Because if you're not using them, nobody else can use them. But the one thing is, it's very easy for the virtual components to be returned to the cloud vendor. Basically, you choose to have a component and then you release it. So a good example for a cloud is an external IP address. These are very short in demand. You say you want an external IP address for your computer. It's allocated when you start the computer. When you stop the computer, the IP address is returned to the pool for use by somebody else. It's so easy to reconfigure for smaller or larger computers. So now we've got the concept of platform as a service, or PaaS. And what this is pre-configured runtime environments, typically operating systems or operating systems plus well-defined applications such as web servers. And these components are cloud-based, and you choose which ones you want. The cloud provider is responsible for updating the hardware and the software to certain versions. So obviously they will only support certain versions of certain operating systems and certain applications for the maintenance purposes. The customers provide the business logic. You provide the code that uses the actual application, the cloud provider provides the rest, and you just pay for the resources that you're using. Software as a service. This is where you get a full-blown application, such as a web-based application maintained by the service provider, and you pay for the usage. You pay for the networking traffic used, storage information, and other things. So now we're going to talk about architecture, which is how things join together. How do systems communicate with each other? There are different definitions of architecture, defined by different organizations. In UML, the Unified Modeling Language, it's the collection of connected units which are organized to accomplish a specific purpose. And what you need is some kind of model which defines how these things interconnect. The IEEE says a system is a collection of components which need to be organized to perform a particular function or set of functions. And software architecture in practice says the software architecture is the structure, or the structure is a program which enable the elements to be connected together and the relationships between them. So what are the goals of architecture? Well, it involves various people, various parties, the stakeholders, the business goals as well, and also the IT infrastructure which needs to support it. As DevOps, the IT infrastructure is the most important aspect of it, but there are the other two to take into account. As DevOps, we'll be concerned with building the infrastructure to support the architecture that's required. So an IT architecture, what is it? Well, it's rules and guidelines and patterns of system development. So we've got to manage the problem as a series of discrete pieces. We need to define the communication interfaces between the pieces. We need to think about the overall structure and how data flows. We need to integrate the various systems and subsystems in the environment together. We need to develop software modules on the best possible design practices and design patterns. We need to control the delivery of software into the system environment effectively and efficiently and reliably. So this compares architecture and design. Architecture is more strategic, whereas design is tactical. The important word in architecture is how. How do things fit together, rather than what do we use to connect things together. We look at programming paradigms and architectural patterns, high-level patterns, rather than algorithms and low-level patterns. We're looking at the non-functional requirements. Architecture is a non-functional requirement. It's a statement of these systems are going to communicate in this way, whereas design is concerned with the functional requirements. What does the system actually do? And in UML, the diagramming language, we have certain diagrams which are more associated with architecture than those that are used for design. So let's look at some architectural patterns. The client-server architectural pattern has been around for some time. The idea is we have a thick client which communicates across a network with some external data storage. The thick client has the user interface, the business logic, and the data access layer all in the same unit of functionality. So the advantage of this is we basically separate all of the code from the data. It enables the server components to be reused. The server components are managed in some central location, and we can optimize the use of infrastructure. It's also quite scalable. So the advantage of this is we basically separate all of the code from the data. It enables the server components to be reused. The server components are managed in some central location, and we can optimize the use of infrastructure. It's also quite scalable. The problem is it doesn't work well with requirements changes. There are security issues as well associated with it. The server is a single point of failure, which means the whole system becomes unavailable if the one component fails. We've also got the presentation and business logic in the same place, which is not a good idea. It's also quite difficult to test and scale in terms of the thick client. Another pattern which is very popular is the n-tier architecture, where n is a number which is usually 3. The great advantage of this is it's completely multi-threaded, so the middle layers can be executed in parallel, so multiple clients can each have their own threads executing it. If the business logic changes, we don't need to change the user interface client code. Typically the client is a very thin client, such as a web browser. We reduce the network traffic dramatically because most of the network traffic is happening between the layers. And we can add additional layers or tiers for various purposes to add layers of abstraction and failover. The disadvantage, if requirements change, we need to change quite a bit, maybe in the middle tiers. The security implications are quite interesting as well because there can be problems associated with the access from the external sources. We've still got server availability and reliability issues, and we've still got testability and scalability issues. Service-oriented architectures are becoming increasingly popular. They have a great number of advantages. Probably the most important one is loose coupling. We have components which can be written in different languages, operating in different environments, which can communicate with each other seamlessly without having to worry about the details. We've got business services can be spread across lots of different platforms, and you just use the service you need as and when you need it. We don't need to know where anything is. It can be anywhere within the corporate network or within the cloud, and we don't need to know the exact location because the infrastructure takes care of it. We can reuse services. If you've got a legacy application, what you can do is put a service-oriented front end on it, and then it becomes part of a service-oriented architecture. It reduces development costs and increases development speed, and it's easier to integrate the business and the IT environments. There are some disadvantages. It's quite difficult to migrate because there are so many moving parts. You need very good control. You need very good auditing and monitoring systems. And probably the hardest one is getting the development and design correct. How do the pieces fit together? How do they communicate with each other? What series of operations is required to achieve a particular business goal. Many people and organizations these days are going towards REST microservices. It's a good foundation for many API designs. REST is actually not a new idea. It's been around since 1996 when the HTTP protocol was first devised. Basically, the World Wide Web is a good example of a RESTful service. So the architecture has evolved over time. The web itself has evolved massively over the 20 years it's been in existence. It focuses on resources and information and not code. What you do when you talk to a REST service is you ask for a representation of information, not for the actual data itself. So components can evolve separately. It's very highly scalable. You just add other services. Development costs is greatly reduced because each piece is a fairly small unit of functionality. And it makes data important. It exposes data as a resource and requires a separate way of representing data. The data and the code are not considered connected. The data is stored somewhere in some form. The code delivers the data in some representational form. The disadvantage is a lot of people are not familiar with the approach, and infrastructures are not really geared up to deal with it, although that is getting better. It also requires a very significant change in the way that developers think about how things interoperate. Another architectural model is the 4+1 view, which is quite an interesting concept. The idea is that different people and teams have different views of systems. So, for example, you've got the logical view is how the end user sees a system, which is in terms of its actual functionality. You've got the development view, which is how developers see it. What are the actual software components and how do they interact? You've got the process view, which is what are the actual processes and how do they communicate with each other? And you've got the physical view or deployment view, which is where the software actually resides on what hardware and what location. And so each of those four views gives you a slightly different picture of the system. So the 4+1 architectural view says, okay, we'll take these four views and then generate the fifth view, the +1, which are the use cases which take the solutions from the four views and combine them together into a single view in terms of use cases.
Hey, want to become an expert in cloud computing? Then subscribe to Simplilearn's channel and click here to watch more such videos. To nerd up and get certified in cloud computing, click here.